I already presented myself in the introduction. That's a pleasure to me to be here to share some of the work that we did jointly with the APFC Association of Landowners. And basically, most of what I will say in my presentation has already been told by Sarah a little bit, but the difference is that we tried to find a kind of standardized procedure in order to make the assessment of cork quality in the field. Okay, so as we have already told today, the main objective is to give the landowner or the forester some support for the cork price negotiation, which is quite useful for the landowner. And it is important to say that in Portugal we use three main methods for cork trade. It's still very, very common that the trade is made before cork extraction, so the buyer offers a price for the amount of cork that he will extract from the stand. And another one is after cork extraction, a cork pile is made. Usually the forest owner is responsible for cork extraction, and the cork is weighted after 21 days, or the cork weight can be estimated from the pile volume. And a third method that is becoming more common is to sell the cork after cork extraction, but the cork is weighted immediately after the extraction, so no cork pile is made, so it's the fresh weight. And these methods have some sources of lack of transparency. The first one is the problem of cork weight that is not going to be treated here. So in method 1 there's no estimate of cork weight, so there's no transparency in the trade. Method 2 we can have a reasonably correct estimation of cork weight, but in method 3 we have the problem to convert cork fresh weight in air dried weight, and this is also a lack of transparency. And then we have another lack of transparency in the trade, that is the cork quality. So the price per weight unit, that in Portugal we use arrobas, 15 kilos, strongly depends on cork quality. And my presentation relates with the cork quality assessment in order to bring more transparency to the trade. Okay. In the beginning, in 1992, the Forest Service, the Portuguese Forest Service, following the Spanish experience, started to propose a sampling scheme for the cork quality price. This sampling was based on individual trees along a zigzag transect, and usually 50 to 60 trees were sampled at that time. And the associations of landowners immediately saw the advantage of doing some type of sampling in the field, and they started to implement this methodology that was proposed by the Forest Service. So in a stand you just put a zigzag. There was not a very standardized methodology to establish the zigzag. It was more or less depending on the size of the property. And then two methods could be used at that time. So some people were sampling each tree that was crossed by the zigzag. So you did not plan in advance how many trees were going to be sampled, or in other cases, from the map, we could determine the length of the zigzag, so we knew how many sample trees we want to have at the end. So the total zigzag was divided in small portions, and the tree closest to the end of each portion was sampled. So in this method we knew in advance how many trees were sampled. In each tree, a cork sample that, following the Spanish, we call them cala, usually with the size close to 20 per 20 centimeters, was extracted from one of the sample trees, and the total cork thickness was measured, either before and after boiling, and the cork then after boiling was visually classified by an expert. So here is an example of extracting one column. So this is one column. And the price of each column was defined by the combination of caliber and quality. And the stand cork price was estimated as the average of the individual cork samples price. But at that time, no sampling error was calculated. And at a certain point in time, we thought that it would be important to estimate the sampling error, because some people were complaining that the sampling was not representative of the whole stand. Then it's where we started to work together. We started to analyze this sampling design that was being used at that time, and we found out that it had some problems. When we started to compute sampling errors, we found that they were usually too high. So the only way to, one of the ways to decrease the sampling error would be to increase the number of trees that were sampled. But sampling individual trees along a transect is not that easy, because we are always stopping and taking small samples, and then you have to carry all these samplings along the transect. And also the associations of landowners mentioned that it would be difficult to make a big increase of the sample size with that methodology, because this would imply more time, and if they would take one day more, it would increase a lot the price, and the landowners would not be able to pay this amount. But we also found that with this data of individual trees sampled along a transect, it would be difficult to estimate some area-related stand characteristics that are important to plan forest management. So if we do a field sampling in order to estimate cork quality, it would be better to have a two-in-one in the sampling to estimate cork quality, and also to have the opportunity to characterize the stand, like basal area, number of trees per hectare, etc. And some parts of the stand were not covered, so this was a biased sample. If we look here, there are some parts, like those parts, that have too many trees, because you have a large amount of the transect that is inside these zones, while you have other zones that do not have any trees sampled. So it's the distribution of the sample within the stand is not very good. So these problems gave impetus to the study of alternative sampling designs that we thought would be good to be based on field plots. And I put plots under quotes, because they could be plots or just a certain number of trees that in statistical language we usually call a cluster. The sampling is usually carried out at the stand level, so usually we don't need to have stratified sampling. So we do a sampling for each stand, so we have a price for that stand that has the cork extracted in that particular year. But if needed, we would like that the proposed method could also be applied as stratified sampling. So the first decision was to substitute the zigzag transect by a systematic grid in order to obtain a more representative sampling. So if you have here the stand, I eliminated the areas that were not cork oak, and then, as Conceição will explain in the afternoon, we would overlap a grid, and then all the points would be our stop points where we would sample trees. In order to be sure that our alternative sampling method was not worse than the previous one, and that we would even prefer if it would be good, we compared alternative sampling designs, so the individual trees, like it was made in previously, or plots, clusters of n trees. Which one of these methods is better, and how many trees, if these would be considered preferable to individual trees, how many trees shall we sample in each stop point, in each plot? Of course, that we knew in advance that the best sampling option, individual trees or clusters, depends on the spatial structure of Cork variability. If there's a lot of variability all mixed in the stand, then the clusters work better than the individual trees. So we had to study the spatial structure of Cork quality variability within the stand. So what we did is that we selected in the beginning, then we repeated it for some other stands, but in the first study we selected 6 stands representing different regions within the country, and we planned 2 samplings. We planned the traditional zigzag, and we planned you planned also cluster sampling based on a systematic grid, and the one I'm going to focus is this one, because we tried the traditional zigzag just to compare, but we knew that the traditional zigzag was not good because it was a biased sample, as I explained before. So in this cluster sampling, what we did is that in each one of the stands we planned a grid so that around 30 plots would be made in each one of the stands. At the end, we found out that in some cases we did not have the 30 plots that were planned in the beginning. I can explain why. But basically, we had around 30 plots. 30 is this statistically magic number. And then in each point, we measured all the trees inside a radii of 30 meters. And in the 20 trees closest to each grid point, we extracted a calla. So our objective was to have a sampling that we knew was too much, okay? So that we could then make the calculation with 20 trees, with 19, 18, to find out what was the minimum number of trees per cluster that we could sample and still have good results. And this research gave results about the best sampling design for Cork quality assessment, but also for the assessment of stand characteristics that I'm not going to talk about today. We measured for each tree the coordinates of the tree in relation to the center of the plot. So we knew the azimuth and the distance from the center, and this allowed us to simulate samplings with different number of trees. If we would like to sample to simulate a sample with 1 tree per cluster, then we would make the calculations just with the closest tree. If we would like to try 2 trees per cluster, we knew which ones were the 2 closest trees to each point, just because we had azimuths and distances. Of course, that this is research. In practice, we are not going to measure azimuths and distances. Yeah, so here, if I was trying a cluster with 5 trees, I knew which were the 5 closest trees, and for those I had a calla, because I had a calla for each one of the 20 closest trees from each plot center. And then the data analysis was quite simple, because basically we repeated the calculations several times using different number of trees per cluster. We knew in the beginning that an aggregated distribution would indicate to sample many plots with a small number of trees, and a random distribution would indicate the need to sample a small number of plots with many trees. So we would like to know if the 6 stands had a spatial distribution of Cork quality similar, or if they were very different. We found some differences, but a certain similarity between them. Of course, that if we want to be very precise when applying the method, we can adapt the methodology depending on each one of the stands. But the problem is that before we sample, we don't know how is the distribution within the stand. So we, in order to have a standardized methodology, we need to know a method that, as an average, works reasonably well for all the cases. Okay? So, with this simulation study, we could compute the sampling error for all the samplings with different number of plots and different number of trees per plot. And again, I don't know why this black screen is appearing always. By using the grid of plots instead of a zigzag, it was possible, as I mentioned before, to establish a fixed radius plot around each grid point, and also to do the estimation of number of trees per hectare, total cork weight, basal area, and other issues as another project that was made at the same time. Okay, so in each one of the trees we measured the total tree height, that is not very relevant in cork oak, and we also measured the height of the crown base, the height of the bifurcation, the height where the stem begins to make the branches, the debarking height, the DBH. All these variables were measured in each one of the trees, and in some cases we also measured the length that is debarked in each one of the branches. And then, in order to compute the sampling error, we need to start by computing the average price for each cluster, and then we have to compute the sampling error as it is common in any sampling. So we compute the average of all the clusters, and then we compute the variance, and then we can obtain the sampling error. So here is the formula for the absolute error. So is the standard deviation divided by the square root of n multiplied by the t-student, and then we establish this error as a percentage because it's what is better understood by people in practice. So the price of my cork is 30 euros plus minus 10%, then they understand what it is. If we say the value of an absolute error is not usually so nice. So once we have the mean and the sample variance, it is possible to estimate how many clusters we need in order to decrease the error. And this is what we also did. So we fixing a certain percent error, we could compute how many clusters were needed for that stand. So with all this data, then we did a lot of analysis, and I sent to you the article where this analysis is published, but I'm going to share some of the results. So each one of these plots is one of the stands that we sampled, and here each one of the lines is one plot, one of the 30 plots. And here I have the mean price computed with 1 trees, with 2 trees, with 3 trees, with 4 trees. And what we see from here is that there are some differences between the stands. Basically, in this stand, we have price, the variability among plots is much higher when we have just 1 tree per plot, but it starts to decrease if we have 2 trees per plot, 3, 4, and when you come close to 5, 6 trees, then it's more or less the same. In terms of sampling, this means that if I sample more than 5, 6 trees per plot, I do not have any gain because the variability among the plots is the same. And if you look to all the stands, you see that more or less after 6, 5, there's not a large variability. In this one, there's some variability, but the variability is small from the beginning. Here, more or less from 5, it's more or less a good number. So with these graphs, we started to have an idea that 5 trees per plot would be a good number, but that we still have a lot of variation among the different plots. So if we have a lot of variation among plots, it means that we need a lot of plots in order to have a small sampling error. So from these graphs, we were expecting a reasonably large sampling error, but we could have an idea that the 5 trees per cluster were not bad. It was not a bad number. Then in this graph, we can see the sample sizes, so the number of clusters that we need depending on the number of tree clusters for different values of sampling error. Here, for instance, you have a sampling error of 20%, and here you have 15%, and very close to the 15 you have 10 here, okay? But you see that if you, instead of sampling 1 tree per plot, if you sample 2, you have you need much less number of clusters. But after 5 trees per cluster, you do not gain by adding trees per cluster because you don't have any more a decrease on the sampling error. And this was more or less the same for all the stands, again with the exception of this one. But even though this with 5, you after the 5 you have a reasonably kind of stable, and you can ask me, why didn't you test it here more than 7? Because this stand had a very small number of trees per hectare, so it would be impossible to sample more than 7 trees, because then we would need to look for trees that were more than 30 meters away from the plot center. So our idea was to sample the 20 trees that were closest to the plot center, but if we needed to go further than 30 meters, that is the maximum distance for a vertex to work, then we would not sample more trees. And here I have a different graph, but that shows more or less the same. So here I have the percent error as a function of the number of trees per cluster for the same number of trees sampled. So here you have, if we sample 400 trees, if we have 200 trees, if we sample 100 trees, and if we sample 50 trees. So you see that after a certain number of trees per cluster, you even, with the same number of colors, you even have an increasing error. So you gain by sampling more than 1 tree per cluster, but you cannot increase a lot that number. So if you just want to make 5 plots with 20 trees each one, it's not good. You have a lot of samples to analyze in the lab, and at the end the percent error won't be good. So you still need to have several plots. And here is a more theoretical issue. So if we compute what we call the inter-cluster correlation, which means if the trees that are within each one of the clusters have a good correlation or not, if it's close to zero, it indicates that the Cork quality is random, and it indicates then cluster sampling is a good sampling design. So, and you see that in some cases is close to zero, in some other cases is not so close to zero. Here, just after 8 trees, you have something close to zero. But this is a good theoretical indication that helped to take the decisions. And finally, this was also very important, we tried to compute the sampling time. So in the sampling time, we had the time to walk between the points and also the time to do the work at the plot level. And less time implies less costs. That's what we wanted to decrease. And if you look here, you find out that if you sample individual trees, usually the sampling time is higher than if you, in each point that you stop, you measure more than one tree. But then, again, if you increase the number of trees per plot, the sampling time also increases. So what we found out is that it's better not to sample individual trees in the generality of the sense, but we do not have an advantage of sampling too many trees in each point. And so the advice that we gave to the Association of Landowners was that it is possible to substitute the traditional zigzag sampling by a single stage cluster sampling without loss of precision, and in some stands with a large increase in precision and with less time consumption. So they can decrease the sampling error without increasing the cost. That was the objective. And we recommended them to adopt clusters of 5 to 7 trees, and most of them have adopted 5 trees. They usually sample 20 clusters with 5 trees per cluster, and they find that the sampling errors they obtain are reasonably good. It's a compromise between sampling error and cost. Sampling is always a compromise. Silviculture is always a compromise. And this methodology, as I mentioned before, has the advantage that by measuring same plots, we can also estimate area-related characteristics, which in the future can be used for forest management planning. For instance, to initialize growth models to predict the evolution of the stand under alternative forest management approaches. So, what happened? The associations of landowners started to apply this sampling scheme, but then they found out that the buyers started to begin the trading very early in the year. Sometimes in January, February, they are already trying to establish to make the business, to establish the price. And so what the associations of landowners found out was that it was much better if they could carry the cork quality assessment the year before the cork extraction, so that the landowner already has the results when the buyers start to discuss the price. And for that, we had an additional problem, because in the last year, the cork still grows, and we need to estimate this growth. we were happy in Portugal because we had a model, a growth model for cork oak that is called the supermodel, that includes the growth of the trees, but it also included what we call the cork growth module, where we modeled the growth of the cork. And by using the cork growth module of the supermodel, we were able to develop the calculus that are needed in order to measure the cork caliber. Caliber is not written the right way. The cork caliber when the cork is 8 years old, and to estimate what will be the caliber when the cork will be 9 or 10 years old. And that's what I will explain here. This is an example with a cork with 9 years. And if we have a cork of 9 years, what we have is that we have the first half year, because the cork is extracted during the growing period. So after the cork is extracted, we still have some cork growth, and we call it the first half year. And at the end, we also have, at the end of the cork sample, near the belly, we also have another last half year. So is the cork growth the year the cork is extracted, before it is extracted. And then you have 8 complete years, okay? And what the supermodel models is the growth of the complete years. And then it has equations that estimate the total cork thickness once we know the thickness of the complete years. I did here an explanation how the supermodel can estimate the cork thickness with 9 years if it is measured when the cork is 4 years old. So it's an exaggeration so that you understand better. So we have the cork caliber at 4 years, and we measure it. And then we have to discount the cork back and the second half years in order to obtain the thickness of complete years. Here, from the thickness of 3 complete years, we can estimate all the following years using the model to predict cork growth. And finally, we add again the cork back and the last half year. If I will have time, I implemented these equations in an Excel file and I will show it to you. If I won't have time to show the calculations to you, I already sent you the file. So, this is an equation to predict the growth of complete cork rings. So, from the thickness at a certain age, here I called it T0 because it's the start, but it can be 3 years, 4 years. You can estimate the cork thickness. If you start, like in the example, with the cork thickness at 3 years, then you can estimate it for 4 years, for 5, for 6, for 7, using this same equation. And then you have the equations to estimate cork caliber. I don't know why I always wrote caliper instead of caliber. I don't know why. To estimate cork caliber and cork thickness in complete years. So the equation is the same. They have been fitted simultaneously. So this is the cork caliber if you know the cork thickness of complete years, and you can also estimate the cork thickness of complete years if you have the cork caliber. So in the beginning we have the cork caliber, we have to apply this equation 3, and at the end we have the cork thickness in complete years, and then we have to apply this one in order to add the cork back and the 2 half years.